Okay, let's kick things off. Today we are diving into a real mystery. Maybe the mystery at the heart of computer science.
A puzzle that really defines the limits of what computers can do, and more importantly, what they can do efficiently.
We are exploring I guess you could call it the intellectual Everest of the field, complexity class NP.
And this isn't just, abstract theory. This is the stuff that underpins scheduling, optimization, and crucially, our entire digital security. It's everywhere.
It really is. Now, to understand NP, I think we have to quickly go back to its foundation, its counterpart, which is class P.
Right. P stands for polynomial time. And these are the problems where you can actually find the solution efficiently.
So you have a guaranteed algorithm, a kind of quick recipe that gives you a definite yes or no in a predictable amount of time.
Exactly. The time it takes doesn't just explode as the problem gets bigger. For P, the core question is always, can we find the answer quickly?
And the answer is always yes. You follow a deterministic step-by-step process.
But now for MP, we change that question. We make a conceptual pivot that moves us out of that known world of P and into this much more mysterious landscape.
We stop asking, can we find the solution efficiently?
And we start asking something subtly, but, well, fundamentally different.
The new question is, if someone just gives us a solution, a proof, a certificate, whatever you want to call it, can we verify that it's correct quickly?
And that's it. That's the moment class MP is born. It's the class of efficiently verifiable problems.
Okay, so we have to clear up the name right away because it's the most confusing part of this whole discussion.
It really is. The formal historical name is non-deterministic polynomial.
Which sounds a lot like not polynomial.
That is the absolute #1 misconception. NP does not mean the problem isn't polynomial. In fact, P is completely inside of NP.
So if you're listening, the most useful way to think about this, the intuitive definition, is to just remember polynomial verification.
Exactly. It's all about how easy it is to check the answer.
Wow.
For now, we don't care how hard it was to find.
And this difference, this gap between the effort of finding and the ease of checking, that's the central conflict we're formalizing here.
It's an experience everyone has had, even if they've never touched computer science.
Right, think about a really hard puzzle, maybe a difficult Sudoku or a crossword, or even some complex math proof you had to do.
The sources mention that finding the solution takes creativity, intuition, it takes a ton of time. It's hard work, it's frustrating.
But then what happens when you're done? Or when, you peek at the answer key?
Well, checking it is a totally different ballgame. It becomes, as the source says, kinder-like child's play.
You can just scan the Sudoku grid row by row, column by column, and instantly see if all the rules are followed. You don't need any of the original creativity.
You just need to follow the mechanical rules. And that huge gap, that difference between solving and checking, is the biggest unsolved mystery in science today.
Okay, so let's get a bit more formal. If the main idea is efficiently verifiable, how do we lock that down mathematically? What does the definition actually look like?
We use what's called a verifier model. And this model makes sure that when we say something is an NP, we're being really strict about the time and resources needed for that check.
And there are, 3 essential components?
3 essential, and they all had to be bounded. First, you need a boundary, a polynomial function that acts as an upper limit on everything.
A limit on what exactly?
On the time allowed for the verification, and this is critical, it also limits the physical length of the proof you're checking.
So you can't just submit a proof that's exponentially long. That would be cheating.
Exactly. You can't be asked to read an exponentially long novel just to verify a simple yes.
Okay, so that's component 1, the boundary. What's 2?
The second is the mechanism itself, a deterministic, polynomial, time-bounded Turing machine. We call this machine the verifier.
And it's deterministic, so it just follows a strict set of rules. No guesswork.
No guesswork at all. It's purely mechanical, and it must finish its check within that polynomial time limit.
And the third component has to be the proof itself.
Right. The proposed solution. We call it the witness, or the certificate. Let's call it SETSA.
So the setup is, you have the question, the problem instance, which we'll call dollars.
And then you have the proposed solution, the witness. And the rule is simple.
The problem dollars has a yes answer if and only if.
There exists some witness dollars that's short polynomially bounded, and for which our verifier machine, dollar, accepts the pair, Z.
I think we need to linger on that phrase. There exists some witnesses.
Yes. This is so important. We don't have to worry about how hard it is to find that witness. We just need to know that if the answer is yes, then a short, convincing proof must exist somewhere out there.
But if the answer is no, then no matter what proof you try to submit, the verifier will always deterministically say nope.
Precisely. It rejects them all.
Okay, this needs a concrete example. Let's use a problem that we know is really hard to solve. The independent set problem, or INDESET.
A great choice. Inset is a classic graph theory problem. You're given a graph network of nodes and edges and a number, KL dollars.
And the question is, does a set of Togolo nodes exist in that graph, where none of them are connected to each other by an edge? They're all independent.
Finding the biggest independent set in a huge network is an incredibly hard problem. But we just want to prove it's in NP. That checking is easy.
So if someone comes up to us and says, yes, an independent set of size Torgel exists, we ask them for the proof, the witness.
And the most natural witness, the most efficient one, is just the list of the Tokolo nodes they claim form the set.
That makes perfect sense. The proposed solution is the proof. So now we just need to design our verifier, the machine $.
And that verifier has a very mechanical three-step job. Step 1 is just administrative.
Like, does the list you gave me actually have Tokolos, and are they all real nodes in the graph to begin with?
Right. A quick sanity check. And step 2 is the core of it. The verifier has to check every single pair of nodes from that list, Zevelmals.
And for each pair, it looks at the graph and asks, is there an edge connecting these two?
If it finds even one edge, it stops immediately and rejects. The proof is invalid.
But if it checks all the pairs, every single combination, and finds 0 edges?
Then it accepts. The witness is a valid independent set of size $2.
Okay, the process is clear. But to be rigorous, we have to prove this whole thing is efficient, that it happens in polynomial time.
Right, we have to check 3 points. First, correctness. Does our verifier accept if and only if Sivert Leveler is a valid independent set? Yes, our design ensures that.
Second, the length of the witness. That list of Tauler nodes can't be astronomically long.
It can't be. If the whole graph has logins, identifying any one node takes about log n bits. So the whole witness, the list of Tauler nodes, takes at most 10 times log n bits.
Which is a very small polynomial, so the proof is guaranteed to be short.
You don't have to submit a book the size of the universe. And finally, point 3, the verifier's runtime.
How fast does it run? Well, the main work is checking all the pairs of nodes in the list.
Right. If there are Diller nodes, you have to check about Diller squared pairs. And since Diller's is, at most, nadir, the total time is bounded by something like Diller squared, maybe $1 to the fourth, depending on how you look up edges.
But the key is that $1 to the fourth is a polynomial. It's controlled. It's not exploding into $2 to the dollars.
Exactly. And since the verifier is deterministic and runs in polynomial time, we've just rigorously proven that inset is in NP.
Even though we suspect finding it is impossible to do quickly.
Right. Finding is hard. Checking is easy. That's NP.
The amazing thing here is that the insight isn't some complex algebra. It's realizing the solution itself can be the proof. Like, a detective solving a crime is hard, but a jury just checking the presented evidence is much, much easier.
That's a perfect analogy. The verifier is the mechanical juror, just confirming the evidence. Dollars follows the rules. Dollars and dollars without needing the detective's creative leap.
Okay, that certificate view really clarifies the intuitive side of things, but now we have to go back to that confusing name, non-deterministic polynomial.
Right. We have to shift from this idea of an easy-to-check proof to the idea of a computation machine.
We need to talk about the non-deterministic Turing machine, or NTM. How is that different from the regular deterministic ones we used for Class P?
A deterministic Turing machine is like a single disciplined robot. It follows one clear path. State A always leads to state B. No ambiguity.
But an NTM is different.
Very different. An NTM, which is a theoretical construct, has what's called a computation tree.
Meaning it doesn't have to follow just one path.
Exactly. When it reaches a point with multiple possible moves, say it could write a 0 or a 1, it conceptually explores every single one of those possibilities at the same time.
So it branches. It's like a machine that can live in all possible parallel universes at once.
That's a great way to think about it. For any input, it's not just running one calculation, it's exploring a huge branching forest of calculations instantly.
That sounds incredibly powerful, maybe too powerful.
Yeah.
How do you even measure time for a machine like that?
That's a key question. And the answer is a little counterintuitive. You might think the runtime is the fastest path to an answer.
Yeah, that's what I'd assume. If it finds a yes on one branch right away, who cares about the others?
But for complexity analysis, we have to be more robust. The formal definition says the runtime of an NTM is the height of its computation tree.
A height. So The longest possible path.
The longest possible path. We're bounding the machine's resources in the worst case. We need to know that every possible path it could take is still polynomially long.
So a polynomial time NTM is one where, even if it makes the worst choices at every step, the total time is still bounded by a polynomial.
Correct. And this leads to this really profound result.
Yeah.
The two definitions are mathematically identical.
You're saying NP, the class of problems with easy-to-check certificates,
Is exactly the same as the class of problems that can be solved by a polynomial time NTM.
which is why it has that name. Non-deterministic polynomial. Okay, so why are these two ideas equivalent?
Let's look at it from both directions. First, if an NTM can solve a problem quickly, why must it have an easy-to-check certificate?
Well, if the NTM finds a yes answer, it must have taken a specific path through that computation tree to get there.
And that path, that exact sequence of choices it made, is the certificate.
The proof is just the list of instructions. At step 5, I chose to write a 1. At step 10, I moved left.
Exactly.
Yeah.
A normal deterministic machine can just take that list of choices and verify that it leads to an accepting state. And since the NTM's path was short, the verification is also fast.
The path is the proof. Got it. Now, the other way. If a problem has a short certificate, like indiset, how does an NTM solve it quickly? This is the guessing part, right?
This is the magic of non-determinism. The NTM doesn't have to work hard to figure out the answer. It just guesses the witness.
How does it guess?
It uses its branching power. We already proved the witness is short polynomially long. So the NTM just, in one step, non-deterministically, writes out every possible short string onto its tape.
So in one of those parallel universes, it will have written down the exact correct list of nodes for the independent set.
Precisely. Since we know a correct witness must exist for a yes instance, the NTM is guaranteed to find an accepting path.
It skips the hard work of solving, makes a lucky guess, and then just has to do the easy part.
Exactly. Once the guess is on the tape, the NTM just switches gears and runs the simple deterministic verifier algorithm to check its own guess. The whole guess and check process remains polynomial.
So easy to check and easy to guess are really two sides of the same coin.
They're mathematically identical ways of defining this incredibly important class of problems.
Which brings us, naturally, to the biggest confrontation in the field. The one that's defined computer science for 50 years, P versus NP.
This isn't just an academic debate. It's a Millennium Prize problem. There's literally $1 million bounty on proving it one way or the other.
We know the basic relationships, right? P is inside NP.
Right. A deterministic algorithm is just a non-deterministic one that never bothers to branch. And we also know that NP is inside EXP, or exponential time.
Because you can always simulate the NTM's branching tree on a normal computer. It takes exponential time to check every branch.
Exactly. But the core question, the million-dollar question is, does P actually equal NP?
Or, to put it another way, is finding a solution fundamentally just as easy as checking one? Is that difficulty gap we feel with a Sudoku just an illusion?
If P yields NP, it would mean that for every single problem where we can check an answer quickly, there must be a secret hidden algorithm to find that answer quickly, too.
It would completely redefine what we mean by creativity and problem solving. What's the consensus on this?
The consensus is, well, it's overwhelmingly strong that P does not equal NP. That gap just feels too fundamental to be an illusion. But proving it has been impossible.
So let's talk about the stakes. The sources call PNP a computational utopia. What would actually happen if someone proved it tomorrow?
The effects would be immediate and just massive. Think about all the optimization problems we deal with.
Like finding the best route for a delivery fleet or scheduling flights for an airline?
All classic MP problems. Right now, we use approximations, heuristics, because finding the absolute perfect solution is just too slow.
But if PNP?
Those problems would just collapse. You could instantly calculate the absolute best route, the perfect schedule with no conflicts. It would revolutionize logistics, manufacturing, everything.
And what about science? The sources mention things like protein folding.
A huge one. Checking if a protein shape is stable is relatively easy. Predicting how it will fold in the first place is a massive computational challenge. If PNP, you can design new drugs and materials almost automatically.
AI would take a giant leap forward. Mathematical proofs could be discovered by machines.
It'd be a golden age of automated discovery.
Huh.
Every utopia casts a shadow.
Right. The negative side. The moment finding becomes as easy as checking.
The entire foundation of our digital security just evaporates.
Because modern cryptography is built on the idea that some things are easy to do one way and incredibly hard to do in reverse.
Exactly. Things like factoring large numbers. Multiplying two big prime numbers together to get a public key is easy. That's the checking part.
But starting with the public key and finding those two original prime factors, that's the finding part. And we assume it's exponentially hard.
Our entire system of online banking, secure messaging, e-commerce, it is all one giant bet that P does not equal NP. If that bet is wrong, all current encryption is broken instantly.
So even without a proof, our entire modern world operates on the practical assumption that P is not equal to NP.
We have to. Because in the real world, we can't build these magical non-deterministic Turing machines. We're stuck with classical ones. And for these problems, that means we're stuck with exponential runtimes.
Which is where this idea of reductions comes in. It helps us organize all these difficult problems.
Yes, polynomial reductions are key.
Yeah.
It's a way of showing that if you could solve problem B quickly, you could use that solution as a subroutine to solve problem A quickly too. Complexity flows from one problem to another.
It lets us prove that thousands of seemingly different problems are all fundamentally connected, all part of the same big, difficult family.
And that idea of shared difficulty brings us to the N bosses of class NP, the hardest problems in the entire class.
If we wanted to prove P is not equal to NP, we'd have to pick one of these problems and prove that no fast algorithm could possibly exist for it.
Which is an incredibly hard thing to do.
Yeah.
But researchers found a workaround, something almost as powerful, the concept of NP hardness.
So an NP hard problem isn't defined by its own difficulty, but by its universality.
Exactly. A problem is NP hard if every other problem in NP can be polynomially reduced to it.
They're like the universal translators of computation. They are, in a sense, at least as hard as everything else in NP combined.
If you can solve just one NP hard problem efficiently, you can solve them all.
And when you take one of those universal problems and you also show that it's in NP itself, that it can be checked quickly, you get the absolute pinnacle.
You get NP completeness. A problem is NP complete if it meets two conditions. One, it's an NP, so it's verifiable.
And two, it's NP hard. Everything else reduces to it.
And this leads to this explosive consequence, what the sources call the house of cards analogy.
If you find a fast algorithm for just one of these NP complete problems,
the entire structure collapses. P would equal NP. Every problem in the class, from protein folding to breaking codes, would suddenly have a fast solution.
That's an incredible idea, but did anyone know if such a problem even existed?
That was the big question until the early 70s, and the answer came from the groundbreaking Cook-Levin theorem. It proved that the satisfiability problem, SAT, is NP complete.
SAT, the ancestor of them all. This is about Boolean logic, right?
Right. You're given a massive logical formula with variables that can be true or false, connected by A and Ds or Rs and nots. The question is there any assignment of true and false to the variables that makes the whole formula come out true?
Okay, so proving SAT is an NP, that's the easy part.
Trivial. The witness is just the assignment of true and false values. The verifier just plugs them in and calculates the result. That's super fast.
But proving it's NP hard, that's the stroke of genius. You have to show that every problem in NP can be turned into a SAT problem.
This is the amazing idea. Cook and Levin figured out how to take any problem solved by a non-deterministic Turing machine, not a roller, and encode its entire computation into a single, massive, but still polynomially sized logical formula.
How on earth do you do that?
Well, you create logical variables to represent every possible thing that can happen at every step of the computation. A variable for is tape cell 5-1 at time step 12. Another for is the machine in state Q at time step 30.
You're literally describing the machine's entire history with logic.
Precisely. And then you build the formula with constraints that enforce the machine's rules. Rules that say, if you're in this state, seeing this symbol, you must transition to that next state. And a final rule that says, at some point, you must enter the accept state.
So finding a way to make that giant formula true is the same as finding a valid accepting computation path for the original machine.
And since the machine only runs for polynomial time, the resulting formula is also only polynomial in size. It's an incredible reduction.
SAT becomes the universal benchmark for difficulty.
It does. And once SAT was proven NP complete, the floodgates opened. Researchers then proved thousands of other famous problems. Inset, traveling salesperson, Sudoku were also NP complete just by showing they could be reduced to SAT.
Proving they're all just different disguises for the same fundamental hard problem.
So to bring it all together, you now have two ways to prove a problem's in NP. You can design a short certificate and a fast verifier, or you can imagine a non-deterministic machine that can guess the solution and then check it. Both paths lead to the same place.
And that just about brings us to the end of this deep dive. We've gone from that intuitive feeling you get solving a puzzle.
All the way to the formal definitions with verifiers and non-deterministic Turing machines.
We looked at the massive million-dollar implications of the P versus MP question, realizing how much of our world would change if finding were as easy as checking.
And we identified those N bosses, the NP complete problems like SAT and the traveling salesperson problem, which really define the upper limit of this complexity class.
It really is astonishing how many critical, real-world problems live in this neighborhood. Scheduling, routing, logistics, all things we rely on, but that we believe are fundamentally hard to perfect.
And we have to circle back to that reliance. We are, as a society, betting the farm on P not equaling NP. We depend on that difficulty gap for our security, for our economy, for managing complexity.
So for the final provocative thought we want to leave you with, consider this. What would change for you personally in your daily digital life if that gap disappeared tomorrow?
If finding the key to unlock your encrypted messages, your bank account, your cloud storage, suddenly became just as fast as using the key you already have.
Every single piece of technology that gives us a private, secure digital life is built on the assumption that this gap is real and permanent.
The answer to P versus NP doesn't just define an area of computer science. In a very real sense, it defines the boundaries of our modern world.